Morning, and so we have studied weak formulations of various equations by Laplacian Stokes system in addition to the standard problems of Laplacian and all that with various boundary conditions, Neumann, like that. So, whenever you get the message is that, so whenever you have an equation in divergence form, try to put it in a weak formulation, and as I said, this is important to check. A strong solution implies weak solution with regularity implies strong solution, and then try to derive the estimate that will eventually prove the uniqueness. And you also see that immediately you do not get a uniqueness, you may have to replace your spaces with small things like Neumann condition you see with quotients in the Stokes system with the real numbers, and Stokes system also the pressure is only defined up to a constant. You can fix by demanding that constant integral of p is equal to 0. You can fix any other constant, but you have the uniqueness in the L2 quotient out by the real lines. So, such things you have to do it. Now, what we are going in this lecture is proving some regularity. So, the regularity is another important and harder aspect of proving thing. So, you are proving the solutions in some Sobolev space. The idea why regularities are required for further analysis on that. Many applications you need better regularity, and then only you can carry out your analysis, one aspect. Second thing, by proving it is in a better and better Sobolev spaces, you will also be able to say that U is actually classical, and it gives you a way of solving classical solutions as well. So, let us do it. So, I will be doing only for the Laplacian in thing, but then there are plenty of results for the regularity. It is a very deep industry studying regularity results. Okay. So, the regularity of weak solutions. Okay. We have discussed a lot weak solutions. I will give a proof when it is a full domain and other domains and even upper half domain, but general domain I will tell you some hints about it. Okay. So, let me start with a theorem. Let U is in H1 of Rn such that minus Laplacian of U plus U equal to F in L2 of Rn. Okay. Anything, I am not even putting any conditions other than that. This is equation L2, F is in L2 of Rn, this equation is in the sense of distribution. Okay. Of course, you can give other meanings, so but we want only in the distribution sense, that is enough. Then, so you started with a U in H1, then U is in H2 of Rn, and you have the estimate norm of U in H2 is less than or equal to constant into norm of F in L2. You can iterate this process further, iterate the process to get, that is some work is involved, get if F is in Hm of Rn, then U is in Hm plus 2. So, you see you are getting one more, you expect H is in M plus 1, but then you have your U in Hm plus 2 of Rn, you getting one extra, and you have the estimate norm of U in Hm plus 2 of Rn is less than or equal to norm F in Hm of Rn. So, You can repeat this, right. If u is f is in C infinity, then you can see and you can derive many results. Maybe we will discuss it that later. We will write. So let me give you proof of this. This proof is easy due to by Fourier transform. So you take Fourier transform of the equation. Okay, Fourier transform of the equation minus Laplacian of u plus u equal to f, because you can take the Fourier transform because u is in L2 and as a tempered distribution or whatever it is. But then you write down this equation minus Laplacian of u equal to u f minus u, and this is in L2, that you understand. Even though you started with u is in H1, so Laplacian is u is not in u is not in H2, you have to prove that, but you get a minus Laplacian u, that component you get. Basically you have to prove that du by dxi is in L2 for d square u by dxi dxj is in L2 for every I n j, but what obviously implies is that minus Laplacian of u. Now you can take Fourier transform. So what will give you is that mod xi square u hat. So you take Fourier transform is in once you take a Fourier transform you get f hat minus u hat, this is in L2, you see. So that implies u hat is already in L2. So that implies 1 plus mod xi square u hat is in L2. This is precisely the condition that u is in H2 of R. And norm of u in H2 is same as norm of 1 plus mod xi square u hat in L2 and that is less than or equal to constant into norm of f hat, you see, in L2, that is same as constant into norm f in L2, that is it. So the first part. Now how do we iterate that process? That is what we are doing. Now assume f is in H1. So first level you assume that f is in H1, iteration process, iterate, this is what I said. So assume f is in H1 and then you can write, this implies my differentiate minus u du by dxi, this you can see immediately, you see, plus du by dxi is in equal to df by dxi, you can do this. This is in L2 now, okay. So by theorem first part of the theorem, okay, du by dxi is in H2, that is what you have proved, that is u is in H3 and you get your estimate. Du by d is in H3 and norm of u in H3 is less than or equal to, that is just a repetition of norm of f in H1, because norm of df by dxi is coming into picture. So that is in H1 of R. So that is a repetition, that is fine. But when you go to, so let me write down the theorem when you go to upper half plane. So this is in upper half plane, upper half plane. This is slightly more involved because you do not have the full xn direction. So, this is your thing. Okay. So, this is your Rn plus, this is your Rn minus, identified with x prime 0. So, any point here will be of x prime xn, and this is your xn. Okay. So, what is the theorem? So, let me write down theorem. Let u is an H1 node. So, it is for a Dirichlet problem. Right. Such that satisfies integral of grade u grade v over omega. Omega is Rn plus. So, you have Rn plus plus integral over uv Rn plus. So, we have done the integration by parts of the equation equal to integral of Fv for all v in H1 naught of Rn plus okay. So, the same result. So, we will prove it for the first part, then for f in Hm of Rn plus implies u is in Hm plus 2 of Rn plus, and you have the estimate, similar estimates, Hm plus less than or equal to constant into norm of f. Okay. So, how do you prove that? So you use reflection. So, I use reflection here, reflection. Okay. So, with a sign change, not exactly reflection. So, you need a, last time in the prolongations we are used here. So, I will you have to prove the steps. Okay. So, define, you need some change. So, you I used a notation here, I do not know, maybe I do not want to use tilde also. So, I use u plus only, u plus of x prime xn is equal to u of x prime xn if xn positive, and here I put a minus sign, you need that, minus of u x prime xn, because you have to satisfy certain equation, minus of xn if xn negative, you see. So, this is what you want to define. It is not exactly as I said reflection together with a minus or negative reflection, you need that one. So, these are the step 1, you have to prove these are all exercises. I will leave some small but trivial. This way you will comfortable with your Sobolev spaces as well, if you are not done. The first thing to show that, first step which you can show, basically you try to compute your du plus. Okay. So, you show that your u plus is H1 of Rn. So, you show that it the reflection, this negative reflection does not change it. So, basically you compute it, compute your du plus by dxi, that is what you want to do it. Once you know what this is, you know that you can write that in terms of the du by dxi of the upper half plane, that is what you do. The step 2 exercise, okay. Yeah, you have to work out, anyway you have to work out if you want to learn. So, that is no meaning in me working out. show that this equation is satisfied. You see, minus Laplacian of u plus u plus is equal to f plus. F plus is definition is similar. Okay, this is in L2, of course. So you satisfy that Rn now. So you can show that f plus is same definition, same definition, and that is obviously in L2. So that is not a problem. The problem you show that this satisfies in the sense of distribution. That is the point. So you show that minus Laplacian of u plus u plus equal to f plus in the sense of distribution, and f plus is in L2. Okay. Then apply first theorem, that is all. First theorem, you get u plus is in H2. H2 of Rn, and which they estimate u plus in H2, this is in Rn less than or equal to constant into no f plus in L2, which will give you, okay, you once you compute it, you will give you norm u in H2 of Rn plus is less than or equal to constant into norm f in L2 of Rn plus. That's all. These are all in Rn. Okay. So the slight difference comes when you iterate the process. Iterate the process. That is where your differentiation. Iterate the process. The difference is here. That is one way you have to think classically quite often, even though it is a distributional derivative. See, when you are differentiating x1 to xn, you are differentiating these directions, x prime xn. But then when you are differentiating, because you want to see what is Laplacian of whether you can take du by dxi. So if you look at the previous proof, you have this equation, you see this equation, you have it, right, you have this equation. Okay, you have this equation, this equation you have it, you see, and that is where the problem, you can't get it in the nth direction, because when you are doing an in nth direction, you have to take differentiation this side along that. So understanding Laplacian of du by dxi plus du by dxi in the Rn the direction, that is means Laplacian of du by dxn will create problem, but there is no problem. So it is easy to check, minus Laplacian of du by dxi, this is straightforward, du no du by dxi, correct, du by dxi equal to df by dxi, that is not a problem, and not du plus by dxi, this is in L2 of Rn plus, that you can get it easily. That is what I said, the differentiation, this is true for all 1 less than or equal to I less than or equal to n minus 1, that is what telling you get it. So at xn equal to 0, you may not have this issue, you may have a problem. So that is what I am trying to say. So this will imply by theorem 1, by first theorem, again first theorem, du plus by dxi is in H2, you see H2 of Rn for all 1 less than or equal to I less than or equal to n minus 1. Equivalently u plus is, no, you do not get u plus is in H3 yet, because you do not know du plus by dxn. So, that I can't do, but you have that one, but you have to prove that. So, we will prove that in a directly from the equation. So, let us see whether I can write it here itself. So, yeah, yes. So, this is a kind of thing. So, this is a trick. So, du plus by dxi is in H2 implies you can take all the derivative. So, if I take your, yeah, it is correct. So, if I take the derivatives, second derivative du plus by, so in particular thing, in particular you get it. So, let me remove this one. So, this is my very clever way of doing in particular du by dxi is in H2 of Rn plus for all 1 less than or equal to I less than or equal to n minus 1. To conclude u is in H2 of H3, you need du by dxn as well. That is what you have to prove it. So, if I, so that will imply, so I can differentiate, you see. So, this will imply if I take my du by d square u by dxk j dxi. So, I am differentiating. So, it will reduce, this is in H1, that is fine, H1 of Rn plus, because I can differentiate, and this is true for all 1 less than or equal to j, this is true for all n, but for I it is less than or equal to n minus 1. Okay. Now, it is just, so for now you, so you have proved all the derivatives are also. So, you see it is all derivative for all j, second derivatives are also in H1. The only thing missing is when I equal to n and j equal to n, because j equal to n and I equal to up to n minus 1, it is fine, but the only one missing d square u by dxn square, you see, that is the only thing missing. But then now you write it from the Laplacian u. So, what is your Laplacian? Laplacian is summation d square u by dxn square, I square, I equal to 1 to n. So, what you write? So, this will, you write it d square u by dxn square is equal to u minus f and minus summation of d square, because this you have already got it, d square I by dxi square I equal to 1 to n minus 1, you see, because all this is up to I equal to n minus 1, no issue. The only thing when j equal to n and I equal to n. Okay. So, that is all from here, and this is in H1 is given to you, H1 of Rn plus, and that implies u is in H3 and Rn plus and the estimate Go through it, you have to study fully, and in the last 5 minutes I will just tell you the general omega issue. Okay. So, let me write it as a theorem and then theorem. As I said, you have to go through it. Okay. The results are true for domains bounded open omega of class Cm plus 2. You need that much 2 regularity extra. If f is in Hm of omega, then u is in Hm plus 2 of omega, and u in hm plus 2 omega is less than or equal to constant f into hm of omega. Okay. In particular, you apply the embedding if m greater than n by 2, then u is in C2 of omega bar, and hence u is a classical solution, is classical. So, let me tell you the some idea of the proof with m equal to 0. So, you start with m equal to 0. You can do this one. So, before that some remarks, a couple of remarks, and then we will come in. Remarks. Similar results can be proved for Neumann condition. Similar results can be derived for Neumann problem. And another important thing you may see, you do not see such features in hyperbolic equation. Do not see such features in hyperbolic equations. Hyperbolic equations. What we have discussed are the smoothing effects, smoothing. We will not discuss much more than this smoothing effect. So, this will tell you a last comment at the end of it by in the. You can also consider more general second order equations. So, let me not do this one. So, everything will not have a. So, the idea of proof. So, you have your domain. So, there you have to classify the estimates, interior estimates and boundary estimates. Interior estimates are relatively easy, not that always easy, and boundary estimates. But boundary estimates are always hard. Even in the classical case of Perron's, Mexide, etc., you have seen that boundary estimate. So, you have to distinguish. So, basically you have a bounded domain here, and then you boundedness and the compactness of the thing, you can have these neighborhoods. Okay. That is the thing you will be doing. So, you will classify, this is your bound u0, no u1, u1, u2 like that, and then you have a neighborhood inside to cover everything, and this is your u0, and take partition of unity, take partition of unity. Okay. So, you get some partition of unity phi I. Okay. Say I equal to 0 to k, and you can write your u as sigma phi I phi I u, I equal to 0 to k. So, this is nothing but phi naught of u, this is interior, you separate it 1 to k phi I of u. Yeah, so, this is interior. So, you see support of E naught u is contained in u naught, which is completely inside, but support of E j phi I, support of phi I is in ui. So that is all, these are boundary, this is interior, you see, that is what I say. And you write an equation, and I call this to be ui, function ui. Ui is your phi I u, and you define, so you can actually see that minus your Laplacian of u naught plus u naught is equal to phi naught of f. You can compute this. So I will just write down here gradient of phi naught and gradient of u minus Laplacian of phi naught u, and this is your g, identify g, which is in L2 of which is in L2 of u naught, you will get it, you can do that one. And then u naught has a support completely inside, and you can extend your u naught by 0 outside, and then you can get u naught tilde, the extension by 0 minus u naught tilde plus u naught tilde equal to some g tilde in Rn, in L2 of Rn by extending, and then apply your thing to get regularity of that one. So you write here. So and you can get your estimates. Ideas are similar here, but you have to do it in a different thing. So regarding this boundary, this is concerned, what do? You transfer to this case. So you have to do this case here, and then you have to do some sort of work here, some extensions and all that, and you can still write your equation, because in Rn plus, the thing is that you transfer this equation here. Since I do not have time, I do not want to skip it, because I do not want to continue in the next class, and you can extend here. But then there is another proof. What the proof I have given in Rn plus is using the Rn, which is given the proof using the Fourier transform, and then that same proof you are given. But look at the reference of Brazis, Brazis, and he has given a proof without using Fourier transform, and that proof can be adopted to Q. So you transfer here, and then that Q plus you can give a proof of the regularity, and then this is gone via G and G inverse. So you have these maps G and G inverse. So from here you can via G, you can come here to this part and use that new proof, different proof, not the Fourier transform proof. Even Rn plus you can give a different proof. You can have the reference of Brazis, and you can still write your minus Laplacian of ui, end of you can write something like that, minus Laplacian of ui equal to g tilde, okay, and you can get similar estimates. So I think I will not do further here, and what one last remark, with one last remark probably here. So this slightly, how do I say the remark? So what you have seen is that you can derive regularity, and in particular f is in L2 of omega, you get something like, or f is in C infinity of omega. So let me check. In particular you can get, if in C infinity of omega, you can get u is in the C infinity of omega. But if you choose omega, any subset of omega, that obviously implies u is in C infinity of omega. So you can get local, of course you are getting global regularity, and getting from there you are deriving some sort of a local regularity. But the interesting final remark what I want to is that you do not need for this particular equation, if f is in C infinity of omega, that will, this is an additional thing. So, you get locally, if you have a local smoothness, you get local smoothness, and this property is known as hypoellipticity. Okay. So, what do you say that elliptic operators a hypoelliptic property. Okay. So, wherever your data f is smooth C infinity, you get C infinity of omega property. So, the Laplacian is hypoelliptic. Okay. But wave equation is not, it will not give you smoothness, in fact you smooth, but the heat equation you get smoothness. So, the heat equation in that respect shares the property of the elliptic operator. The smoothing property is there for the heat equation. That kind of phenomena you will see anyway in the lectures. So, I will stop here. So, in the next maybe 1 or 2 lectures we will do some maximum principles. Thank you.